Neutrons are radioactive. You know, the neutral particle in every atom except hydrogen? Yeah, it's unstable. And if that isn't weird enough, we don't even know how long it takes them to decay. Depending on how you run an experiment, you get different answers. Weird, right? But worry not, the neutrons in your body are fine. They're confined to the nuclei of your atoms, and when they're in a nucleus, they're held together by the strong nuclear force, so they're completely stable. But occasionally, when something radioactive decays, they give off neutrons that fly freely, not trapped in the nucleus of an atom. And these neutrons don't last forever. Instead, they decay into a proton, an electron, and an electron antineutrino. And they last, well, about 10 minutes and 11 seconds. And I say about not because I'm rounding, but because we don't actually know what the half-life of a neutron is. See, there are two ways to measure the lifetime of a neutron. One way is to produce a slow beam of neutrons, say from a nuclear reactor, and measure the amount of protons given off by the beam. If you know how many neutrons are in the beam and you count the protons resulting from the decays, then you can measure with high precision how long the average neutron lasts. And you get nearly 10 minutes and 15 seconds. But alternatively, you could just fill a magnetic trap called a bottle with a certain amount of very cold neutrons and then just count how many remain after waiting a certain amount of time. This also allows for the determination of the average lifetime of a neutron, and you get nearly 10 minutes and 8 seconds. Now, 7 seconds of difference wouldn't seem like much if the error bars were fairly large, but they're not. In both cases, they're on the order of 1 second, meaning that the probability that it's somewhere in between is about 1 part in a million. And unfortunately, this is not one of those cases where theory can come to the rescue. Calculating the neutron lifetime from purely theoretical considerations is still impossible with current methods. So is this a hint of new physics? I'd say probably, but who knows what that might be.